live or alive? So if you took a point, let's say it was 2, 4, and that point was a part of some figure, like a triangle or a star or a doghouse, whatever shape. If you took that point and then you applied a size change to it, you would be multiplying the x and you would be multiplying the y value by something. So let's say you're going to make it twice as big. Then you would have to multiply it by 2, yes. If you're going to make it half as big, you'd multiply each of these by a half. So, let's say we make it half as big. Then what we would do is we would take a half times the 2, and then we would take a half times the 4, and then we would end up with an image. So this is the pre-image, what we start with. We've been calling it that for a while. And then this is the image. And your image in this case is going to be what? 1, 2. So if you come over and you go up, 1 over and 2 up, so this point got moved back towards the origin. And maybe you remember, but if you don't, whenever we do size changes, the image and pre-image fall on a line that goes through the origin. Everything does. So that's what they're showing in this picture here in example 1. Let's see. Can I go bigger? I can't just go bigger. So in the book, we're showing how R and R prime, they end up being on a line that goes through the origin. T and T prime, this point and this point, there's a line that goes between the two of those that also goes through the origin. That's one of the things that we did with all of the rotations and reflections over the x and the y axes. Last year we did a sailboat like this. Do you remember the sailboat? And that sailboat has all the corresponding points of the large and the small sailboat falling on lines that all go through the origin. So that's part of the definition of a size change. They talk about when you multiply all of the x and y values by some k value, which is the magnitude of the size change, that they all have a center of 0, 0. That's part of this definition. So the size change here, a k value, would be like the half. So if k is equal to 1/2, multiplying both the x and the y by the same number is what gets done. We don't multiply them by different numbers. It's by the same number. So you're making it twice as big or 10 times as big, but it has to be in both the horizontal and the vertical components. So if you were going to write just like this 2, 4 as a matrix, how would it look? It's going to be 2 over 4. It's going to look like that. So remember that all of your x's are going to be on the top and all of the y's are going to be on the bottom. So for example, this triangle here that's in example 1, that triangle can be written as a matrix, a point matrix. I need it. There we go. Let me get rid of this. And let's take that triangle. They want us to look at the magnitude of the size change. So we would be looking for the k value. And then they want us to write it with mapping notation. I want to go a step further, and I want to write it as a matrix as well. So first of all, what's the magnitude of the size change of this triangle? So it starts out with a little one, right? And then if you just look at the r values, the y of the r point, that's 4, and it goes all the way up to 16. So you'd have to multiply by 4. So k is equal to 4. So that means that every one of the points here, negative 1, 2, they get multiplied by 4 on the x and the y, and so forth with the r and the I as well. So let's write that as mapping notation. Remember mapping notation? Say either yes or no. No? Okay, so with mapping notation, what we do is we have to include what we start with, which is what is x and y. And then we use an arrow, or sometimes they use an equal sign, but an arrow is most commonly used. And what that is going to do is it's going to say that every x and y is going to change into like kx, ky. And we put a big S in front of this with a little k and then a colon. So that's the general form of mapping notation. So in this case here, because k is equal to 4, oops, that's not what I can put that there. We say S of 4 of the points x and y. In other words, a size change of 4 acting on all of the points with the ordered pairs x and y becomes 4x, 4y. So that's mapping notation. This is how it changes on the graph. So let's do this. Let's write a matrix for this triangle TRI. So we'll put T and then R and then I here. So the ordered pair of T is going to be these two numbers. What are they? What are the x and the y values for T? Negative 1 and 2. And then the x and the y for R is 1 and 4. And then the x and the y for the I are 1 and negative 3. So curious. What kind of a matrix that would have k values could we multiply by this to get a new matrix that's going to look like that image? What would be the shape of the matrix that you would use to multiply by each of these points? Well, if you did a 3-row by 2, yes, you could do that. But it doesn't have to be that complicated. All we're worried about is multiplying each of the x's and the y's by a 4. So if we do them one at a time.
3 by 1. Would we technically then?
Well, 3 by 1 would be too big. Because if you had a 3 by 1, you'd have 3 of them like this, and you would turn them, and then you would multiply by each of that. But then they'd be added up. 1 by 2. Look at if you had something like this. So if you took this matrix and you multiplied it by these two, then you could have your T prime over here. So size change matrices are just 1 by 2s.
Why can't you just do scalar? Why can't you just put the 4 in front of it?
You could do that too. You could just put a 4 in front of it, and then it would be a scalar matrix. We want to be thinking, though, in terms of this here. And we're going to make this a little bit more complicated than this before this lesson is over. So this is just to give you an idea of how we get to where we have this image. Let's go on to the next example. Eventually what we're going to do is we're going to work with 2 by 2s, because 2 by 2s are really powerful matrices for doing lots of inverse operations as well. And that's what we're slowly heading into. All right, so graph paper. Why don't two of you guys make sure you do different. Maybe Willow, you can do the 2, and Taylor, you can do a 3rd, and Avery, you can do times a 3rd, and Logan, you can do a 2 And then you can choose which one you want to do, but you'll have to compare with somebody else. So what we need to do is begin on your graph paper, put this little polygon on, and then what we're going to do is you're going to write a matrix that represents it, sort of like what I did here. And then you're going to take these 2x2 matrices and you're going to work those. And you'll see how it's a little bit cleaner than what you would have if you had a 1x2, or yeah, 1x2. So let's do the point matrix together, unless you want to work ahead of me. It's called NUMER, so let's put them in that order. NUMER. So how is this matrix going to look? It's always going to be, think of this as multiples of 2x1s, because each point is set up vertically with the x over the y. So we've got 5 points here, so that means we need 5 x's across the top and 5x or 5 y's below. So that's a 2x5, not a 5x2. Rows by columns. Rows times columns. So n is going to be 4, 2. What's u?
6, 2.
And m?
6, 6.
And e?
3, 4.
And r?
4, 4.
Okay. So once you have that graphed, then take this matrix and you're either going to put the 2, 0, 0, 2 or the third in front of it. And if you do that, if you have a 2x2 instead of a 1x2, then when you add, and this is an important idea to look at, if you take the 2 and the 0 and you multiply it by 4 and 2, you're going to take 2 times 4 and 0 times 2, and that is going to be this element right here. So you're going to, if you're doing the 2, you're going to end up with an 8. So what ends up happening when you use a 2x2 instead of a 1x2 is you're multiplying 0 by the y, and then when you come across the second time to get your second row here, you're taking 0 times the x value and you're only multiplying by the 2. Can you see that? Or is it awfully early after a 5-day break? Multiply them through. numbers. All you're really doing here is you're taking that 1/3 times each of these top numbers and then you're going to do the x values for the image. You take a third times 4.
Okay.
When you guys are multiplying these fractions, like a third times 4, just write 4/3. Keep it simple. No decimals.
So
You got to take
is
it.
it gonna be 0 on the bottom for all of them?
Yeah.
Okay.
Yeah, so when you do this 2 times the 4, it's 0 times the 2, you're in essence, you're never multiplying the y value. Because you take 2 times the 6 then, and 0 times the 2, and 2 times the 6. So it's really just taking 2 times each of these top values and going straight across.
And then you add them,
You don't do any adding after this, so
I mean, like, combine the, anyway.
yeah, the 2 times the 4 and the 0 times the 2 get added to make the
Oh, I
8.
see.
The 2 times the 6 and the 0 times the 2 get added to make 12.
Okay.
And again, 2 times 6 and 0 times 6. And 2 times 3. But it's 0 times 4.
And then you go through the second time with the other one to get the
Yes,
bottom value.
then it's 0, so now you're not
Okay.
multiplying the x value. You're just taking this 2 and multiplying it by each of your y's. So 0 times 4 plus 2 times 2. 0 times 6 and 2 times 2. And so on. So the matrix multiplies out pretty quickly. And then if you do the same thing times a third, then you're just taking a third times 4 plus 0, a third times 6, and so on. And then you're just really multiplying a third by each of the bottom values. And yeah, you can do it with your calculator, and yes, you can force it out to give you fractions as well. Once you get the matrix in front of you, if it shows up as decimal, then you go to, is it math? And then with the fraction decimal, and then the first option, you hit enter twice, and then it changes your matrix. So, and then you don't have to plot a whole polygon if you don't want to. You can just plot a couple of points. And you're going to take this and put it on here. And you should see that everything is twice as big.
Oh, never mind. I'm just
So now,
blanking.
yeah, so now there's your new matrix, and if you plot it, then you'll see that it's a third the width and a third the height, or twice the height, twice the width. But you're also going to find that going through the corresponding points like M and M prime, a straight line is going to go right through the origin. Because any size change is going to have that happen to it. You're going to have that line that runs through the origin. Ooh, I wrote example 1, that's not example 1. those lines, there's a name for it. They're like not coincidental. Maybe they're coincidental because they all cross at the same location of the origin. About that? Really close. How you doing? You got it. Okay. Boy, you're walking pretty fast on that knee. I must be ready to go, huh? Don't slip on the ice.
Yeah, it's pretty scary.
Yeah. Joe got out of the vehicle the other day after skiing, got on the driveway, like the worst place in our driveway, steps out, went down like a pile of bricks. It makes me scared every single time. She's got a new hip, but it's a year and a half old, but still, she falls on that thing. She does stuff to it. And then yesterday she went through a whole bunch of, she was going over snowshoeing, and there's a big pile of logs, and she went down through it all. And I was like, tougher than me. Okay, so size change theorem. These are the K values. When we use matrices to do size changes, we use a 2 by 2. And it's always going to be, I can't write today. Always going to be a 2 by 2. It's going to be set up like this. So I think for most matrix operations from now on out, as I teach them to you, this is what we get to use as a multiplier. That's going to be our factor.
Would it matter which order it's in? Like, could we technically have it flipped so 0K, K0?
Then if you did that, then you'd put all your y's up on the top. See, then you would be taking and multiplying the bottom row and turning it into the top row.
Okay.
So that would be changing your x's into y's,
Oh.
and your y's into x's. And that would be a reflection over the y equals x line.
Okay.
And that comes up.
Okay.
So yeah, you reflect over y equals x, and then it's a 0k, k0. Yes. But let's not worry about that just
I
yet.
just didn't know if it would change it then.
Yeah, that does change it. It does, but that's good if you can see that. So here's what they give us. They give us a size change of 4. And they say, well, it's something 0 and 0, 4. So what has to go here if we're going to do a size change of 4 using this? You have to have a 4 there, yeah. Okay, and then if we're going to take this original matrix that we were using, that triangle from example 1, that was something blank, and that's a 2, and they give us this much, and they say it changes into a negative 4, something, and then a 4, something, a 16, and a something. So we have to fill this all in. That's what this is about. Now, you're going to see homework problems that are going to be like this, but they're not going to tell you what the size change is necessarily, or what the image and the pre-image are. And you're just going to have to figure it out line by line, breaking these matrix multiplication problems down into linear problems. So if you have 4 multiplied by something here and 0 multiplied by 2, and that gives you a negative 4, this means 4 times that x is equal to negative 4. Therefore, x has to be negative 1 in that case. And if we get all the way down here to where it's 4 times a value plus 0 times the negative 3, 4 times that, and that has to be a 1, because the 4 times the 1 becomes a 4. And then, if we take 4 times 0, well, this 4 times this 1 and 0 times whatever's here, it doesn't matter what's here. 4 times 1 will be 4. So this is supposed to be just an exercise in seeing these things. And then we take 0, 4 times the first one. What has to go for the y value of t prime? 4 times 2. And then to get the y value of I, we would take 0 times 0 and 4 times negative 3. It's negative 12. Then all we have left is this point here. So 0, 4, yeah. That's what number 2 is all, or example number 2 is all about. Okay, you guys remember the Pythagorean? I hope so. If you don't, you think about it a lot. Ooh, not an R. What's the Pythagorean? A squared plus b squared equals c squared. But when it comes to the distance on the coordinate plane, the distance between any 2 points, between A and B, is going to be equal to, how do I write it now? Here, let's come over here. You guys said it's a squared plus b squared equals c squared? Oops, let's do it this way. So here's your A and your B, there's your C on the left. You don't like that, do you?
Well, it's,
I wrote equals too, didn't I? I'm writing it backwards. There we go. That's better. Yeah. You should write some of this down just for the heck of it. You just never know when you're going to need it on the homework. I don't know. So if you're on the coordinate plane, a triangle is going to have a vertical change and a horizontal change. And that vertical change you could think of as A, and you could think of the horizontal as B, or vice versa. It doesn't matter. But on the coordinate plane, this, using the distance formula, is the difference between the y values. This is the difference between the x values. So you know what I'm going to do? I'm going to change this to B and to A, because then it might be a little more consistent with the order that I put it here. So you're going to have x sub 1 subtract x sub 2, quantity squared, plus y sub 1 subtract y sub 2, quantity squared. So there's what you need to do. The other option is to think of this as the absolute value. You can go either way. It's kind of weird. The Algebra 1 book, it does it with parentheses. And then in this book, it goes to the absolute value. Absolute value is more formal, but you're going to get the same thing either way. So however you wish to look at it, you're fine. Just realize that they mean exactly the same thing. So that's, this ends up being like the AX value, and that's the BX value. This is the AY, and this is the BY value. Because what they're doing is they're saying that these points, A and B, and we're using this to find the hypotenuse length. But these points, A is going to be x sub 1, y sub 1, and point B is x sub 2, y sub 2.
since there's technically like the absolute value is squared and then top the square root, technically can't we get rid of both of those? Or do they need
No.
to be-
No, you have to find the difference first. And the difference is what gets squared.
Okay.
Yeah, no, you can't just, and then they're being added, and because the because the radical, the square root, is a grouping symbol, you have to do the addition underneath here first. You will not get the same value otherwise.
Right, I forgot about that.
Yeah, So don't go and take the square root of each of those and just add them together. That only works in a few unique cases. It's not the rule of what we do. Okay, so we're gonna get this thing done. You might have to look a little bit more carefully at this last one here, but they talk about similarity in size changes. Everything we've done here, we've ended up with similar figures. And you may recall from geometry that with similar figures, you have the same shape, but not necessarily the same size. Same shape and size is called, that's congruence. We get that from reflections and rotations. But we don't get it from size changes or stretches and squashes, which we can also do with matrices. So the ratios of everything with these figures are going to be equal. So with this little half-house shape here, when you multiplied by 2, 0, 0, 2, all of the lengths ended up being twice as long. It was twice as tall. This from M to R was going to be twice as long. And it's twice as long because of the Pythagorean. So to kind of, in a short way, explain this last example, you're able to take points in a size change like this, and you're able to use the Pythagorean to find that whatever your size change is, these points end up being that change in distance away from one another. Just like points that are on the vertical axis or on the horizontal axis do as well. And that comes from this idea that when we have like Pythagorean triples, like 3, 4, 5 is a Pythagorean triple. 6, 8, 10. And then we can do 9, 12, 20. Is that right? No, 9, 12, 15. So the Pythagorean triples, if you multiply each of the sides by the same value, by the same size change factor, you end up with another right triangle that has the same ratio of side lengths. They're proportional to one another. So that's what they're getting into at the very end here with triangle TRI and triangle T prime, R prime, I prime. They ask you to go and calculate and measure all of these lengths and changes of lengths. But that, I'm not going to actually take time to do it. I mean, you could just, quickly in your book, you could just take a ruler and put it on here and see that this is going to be 4 times as long as this length. This length from R to I is going to be multiplied by 4 to get R prime to I prime. So we're kind of revisiting some of the geometry ideas, but then we're just doing the work with matrices. That's it. So I have 1 through 12 and 15.